If we could understand how that pup maintains this wonderful control of its metabolic fuel supply, we could stop type 2 diabetes. On the other hand, the mother seal, in those same 4 days, loses 50 pounds of pure fat. Who wouldn't like to know how to lose 50 pounds in 4 days? It's in the model. So that's what we've been doing. So let me tell you what we've been doing with humans and what makes, in essence, the entire point from beginning to end. Katie Hind, anthropologist, she keeps reminding us it's a conflict. The mother is dissolving herself. Everything, including the water, is expensive. If it doesn't profit the infant, it'll be gone. So we start taking milk apart, and we find a paradox. Lo and behold, human milk, the third most abundant component, is completely undigestible by babies. Why would mothers dissolve themselves to make something that's undigestible? Made no sense. So first we had to figure out, what is it? So again, the joy of being at UC Davis, Carlito Labriglia, the most successful, famous analytical chemist in biopolymers in the world, he takes on the challenge. What are they? He constructs analytical platforms. It turns out milk is full of oligosaccharides. These are sugar polymers, very discrete sugars held together by stereospecific bonds. And there's about 200 of these structures. Carlito builds an analytical platform to measure all of them in high throughput. So now we know mothers are dissolving themselves to make sugar polymers. Why? The babies have no enzymes to break them down. They go right through the baby. So the next question, of course, is why would they do it? What possible value would it be to the infant? Well, my theory was that if they don't feed the baby, they must feed bacteria. And it's the bacteria they're feeding on. And so, again, we recruited world-famous microbiologist David Mills. He studies bacterial ecology, everything from wine vats to the human intestine. Gave him the oligosaccharides. Do bacteria grow on these? No. He broke my heart. He tried bacterium after bacterium after bacterium. They don't grow on them any better than babies do. But then he found one. Oh, what a surprise, from the intestine of a breastfed baby. And we sequenced the entire genome of this bacterium, and it was remarkable relative to even its very close genetic ancestors. Bifidobacteria. It's a Bifidobacteria longum, subspecies infantis. It has 700 genes different than other Bifidobacteria. When you start mapping the genome, every one of those oligosaccharide sugar linkages, for which babies and bacteria have no enzymes for, Bifidobacteria infantis has genes encoding every single one of them. This is clearly an evolutionary symbiont. This bacterium, in essence, evolved to live in a very unique ecological niche, the intestine of the breastfed baby. What an idea. Mothers literally recruiting another life form to babysit their baby. And they're making sure that only one bacteria thrives because that's the one they feed. Oh my gosh, what an idea. This is 4 PhD theses. It's a poopogram. The top, these are the oligosaccharides in one particular baby. It's several periods during the first few months. And you notice in this baby, the beginning, oligosaccharides go in the baby, oligosaccharides come out of the baby. Day after day, week after week. And the bacteria in the baby are not the kind of bacteria you'd like. Gram-negative Staphylococcus, Streptococcus, coliforms, really Clostridia, bacteria you would not want in a baby. But then, in this particular baby, after about 3 to 4 weeks, it got inoculated by means we do not know with Bifidobacteria infantis. Then the oligosaccharides began to disappear, and Bifidobacteria infantis increased and increased and increased until it completely dominated the ecology of that baby. And that's what we see time and time again. If a baby is breastfed, basically the only food supply in its intestine after the baby has absorbed everything else are these complex oligosaccharides. And if infantis is there, boom, it grows and grows and grows. Over 90% of the biomass in the diaper of these babies is a single strain of bacteria. It's a remarkable idea of evolution. So, who would use this? Well, first, breastfeed, breastfeed, breastfeed. This is only possible with breastfeeding. There's no other, in essence, way to do this. It's a remarkable idea of evolution. It's only recently we've realized how important this is. So encourage everyone you know to support breastfeeding. But there are some very obvious customers. Mark Underwood, head of neonatology at the UC Davis Medical Center. Imagine his daily life. He takes babies who are premature, born typically by cesarean section from their mothers. Cesarean section means these babies are born sterile. They have no bacteria. He takes them into an incubator and then starts to grow and nourish them, but then they start to acquire bacteria on and in them that will live with them for the rest of their lives. And where are these bacteria coming from? The hospital. This is not the way you'd like to start life, especially as a young premature infant. So, together with Mark, we asked the question, if these premature babies got human milk oligosaccharides and they got the bacteria appropriate to full-term babies, would this bacteria grow in them? Absolutely. Grew, dominated just as if they were a full-term baby, and protected these babies from the sorts of diseases they get, necrotizing enterocolitis, sepsis. So a remarkable strategy. So we knew this is something that we had a customer for. So we actually went to a variety of companies who produce bacteria and said, you should make this as a product, sell it to the NICUs, and they all said, sounds like a good idea. How many NICUs are there? Well, there's a few hundred. Total? That's not really a market, is it? It's an orphan. So no one would take it on. So the faculty who were involved in it decided, well, frankly, we're all tenured, so we mortgaged our various assets and started a little company to productize this for premature babies in the NICU, and away we went. But what we realized then is mammals have a remarkable strategy at birth. Live birth confers a remarkable asset to the process, is that mothers can transfer the bacteria that they've acquired in lifetimes to the baby. And in fact, birth is, apologies after dinner, it's a bacteria transfer event. All of the bacteria from the mammalian mother go on to the baby. And that really does provide a significant advantage. What a great idea. But there's a flaw. Modern medicine, with the best of intentions and outcomes, have used antibiotics to save mothers and babies, have used cesarean sections to save mothers and babies, have used infant formula to rescue babies who could not be fed by mothers. But there was a consequence. They stopped the transfer of the bacteria to the baby. And we've basically lost this bacteria. We have not found a baby in the greater Sacramento area that has the bacteria. It's basically been lost. Problem. So now, in essence, we are encouraging people that this now isn't just for premature babies, even just for C-sections. We have inadvertently dropped the ball on this bacterium. The good news is you can put it back. So this is a distribution of cohorts around the world. And if you'll notice, where modern medicine, antibiotics, cesarean sections, infant formula have not reached yet, those babies are still, in essence, dominated by Bifidobacteria infantis. But increasingly, as modern medicine penetrates the country, down goes Bifidobacteria infantis. And interestingly, up goes allergy, asthma, atopy, eczema, all the conditions of a maldeveloped immune system, autoimmunity. Metabolic conditions start going up. Obesity, diabetes, as the metabolic regulation that occurs during early life is displaced. So we think that many of the conditions that we're seeing rising in the Western world associated with the most affluent children in the world who should be very healthy but are paradoxically getting asthma, allergy, all of these conditions, it's because that window of life, early, first year, when they had this wonderful protection system in them, the combination of breast milk and this bacteria has been lost. And we can put it back. So what have we learned? We've learned that the bacteria in us is very important. It provides a variety of protective, nutritive, and even metabolic signals to us. It's critically important according to evolution. There's more oligosaccharides in human milk than protein, which that means from an evolutionary perspective, it's as important to feed the bacteria in the baby as the baby. And that's going to be true for all of us. And we are doing nothing to recognize the bacteria in us, what should we be feeding those bacteria in us, and what could they be doing for and against us. So what that means is the world of food is going to change. We're going to have to start, in essence, putting bacteria back into all of us. And it sounds horrible. Who would want to eat bacteria? Well, it turns out, not so much. So if you look at the great foods that have emerged from the history of cuisine, chocolate, coffee, beer, wine, cheese, yogurt, bread, they're not commodities. They're a combination of a commodity plus microorganisms. And the combination of those two acting together increases the safety, the nourishment, the stability, and the deliciousness of those products. So in fact, as we move microbiology and industrial organisms into the food supply, as we nourish the bacteria in us and improve the way they can protect and enhance our performance, the food supply will get more stable, more nourishing, more safe, and more delicious. So it is a good future. So let me give you another example of what this model is doing that's helping us understand both babies and the rest of us. So now that we realize how big a challenge premature babies are, in 2017, 12% of babies in this country will be born premature. This is a massive increase in the subpopulation. And if you're born premature, you have a much greater risk of developmental problems and degenerative problems. So we need to understand, how do we nourish these babies? So we had a simple question. These babies are premature. Can they even digest milk? Right? We've always assumed, give people food, they digest it in their stomach, absorb it, good to go. But babies are premature. They don't have developed stomach. Their enzyme systems, have they even developed yet? So we had to ask the question, can babies digest milk? So in order to do that, we had to reach into a baby and take the milk back. Well, that's why it's so nice to have Mark. So as a neonatologist, he does that routinely. So we could take milk proteins, measure the peptides that are released as a digestive product,